The method to plot the loop gain is nothing but what we did is like we first took the open loop transfer function, and in that open loop transfer function I think this is L, we took the open loop magnitude and later on we plotted our closed loop magnitude, okay, onto the same magnitude plot. Now what we did is we try to extract the difference of these two things, the closed loop and the open loop, and that is how I get the magnitude plot of my loop gain. Okay, is this particular process clear? Whereas in the case of a phase plot of my loop gain, we retain the phase plot of my open loop system itself. So both these plots are same, provided my beta is not introducing any kind of phase. Okay, so provided there is no phase from my feedback network. Is that is clear? So if that is the case, I can translate it as it is. Clear? Now, since you already said you know the definition of this phase margin and gain margin, what do we exactly mean by this gain margin? Okay. So in this case, you could be able to see that there is a phase plot. Okay, this phase plot intersects this 180 degree line. Okay, and I'm reading this 180 degree intersection line as omega px, which is nothing but the phase crossover frequency. Clear? Now at this particular frequency, I'm trying to read the magnitude of my loop gain. Now the difference in the magnitude of 0, whatever the magnitude value that I have at omega px, is termed as the gain margin. I think you know about this. Okay, but out of this we are concerned more about the phase margin, and we'll be using more of phase margin rather than the gain margin. How do we read the phase margin then? Which frequency I need to concern? In the previous case, for the gain margin, I took the phase crossover frequency to analyze the entire thing, right? And you probably know it, but we will not talk about much about the gain margin as far as the course is concerned, but we are concerned more about the phase margin. Okay, so how do we read the phase margin? Which frequency will use it? Yeah, so what do we mean by gain crossover frequency? Yeah, it is the frequency at which the loop gain magnitude becomes 1 or 0 dB. Okay, now that is the frequency I've taken, and on that particular frequency I'm trying to read the phase margin. Okay, now this phase margin is defined as 180 degree plus the phase value that you are reading at gain crossover frequency or omega gx. Okay, is that is clear? And now if this quantity is greater than 0 degree, then you would end up having a stable system. Okay, in case, so this is a stable system. In case if it is equal or if it is lesser than this 0 degree, then your system becomes unstable. Okay, and provided if this is my definition. Okay, now we will try to have some two problems, and there is one important phenomenon that happens based on our phase margin. And regarding the significance of the phase margin, I will talk about it when we discuss about the second problem. Okay, so as far as the first problem, can you tell me what is the phase margin of this particular system where I have a single pole in the feedback? What is the minimum phase margin value that I can get it? Minus 45 or? Okay, let us take a simple first order system, because we know this is my A of S, and I know that there is a single pole, and that is what has been given here, and let me label this single pole as something like omega p1, and this is the logarithmic scale of omega, and I just want to plot the phase value, so I'm just doing the same thing. Okay, now at this particular frequency, what would be the phase value that I would get? Yeah, it is minus 45 degree. Okay, and after a while this magnitude would go down all the way, and this has a decaying factor which is minus 20 dB per decade. And what happens after I move to 10 times that of the omega p1? Yeah, so the total phase shift would start here and somewhere here it starts to deviate from 0 degree, and then it moves across this 45 degree, and when I try to reach this particular frequency, it almost attains a maximum value of minus 90 degree. Okay. Now the question is, what is the minimum phase margin that I can have for the system? So let us try to bring our phase margin formula, which states it is 180 degree plus the phase. Okay, so which phase we are talking here? Yeah, what I have plotted is my open loop system. Okay, yeah, yeah. Okay, so okay, because anyhow that doesn't matter, because beta is not inducing any kind of phase value, so I can look for this particular phase itself. Okay, and the point is, I'm not given anything about the factor beta. Now if that is the case, what value you would consider, because everything is always in the under the worst case condition. Okay, so in this case I have never mentioned anything with related to my beta. Now if I am not giving the value of beta, then it is not possible for us to identify the value of omega gx. Am I right? Yeah. So now what value of beta I need to consider then? Yeah, that is the worst condition, because having a beta that is equal to 1 exposes all the poles in my system. Okay, so which is above 0 dB. Okay, so it is always the worst condition is having the beta equals to 1. And if I have beta equals to 1, then my closed loop would have something like this, and the difference of these two plots, which I make it with green shade, would give me the magnitude plot of my loop gain. Clear? Is that is clear? Yeah. So now what is the minimum phase margin that I would get? So you can see here, this is my gain crossover frequency, and when I look for the gain crossover frequency, it obviously intersects with my phase at minus 90 degree. Okay, so what is the phase margin that I would get? So 180 degree minus the phase value at omega gx, which is 90 degree. So it's a positive quantity. Is my system stable? Yes, the system is stable and it's a positive quantity. Is that is clear?